Hello, everybody. Today I want to talk about something that is more conjecture than actually hard-proven fact. In particular, that is, why does SHA-3 not squeeze? So SHA-3, unlike SHA-1 and SHA-2, follows something known as the sponge construction. Now, in the NIST recommendation for SHA-3, it recommends that you follow multiple rounds of absorbed followed by only one round of squeeze. Now, the actual sponge construction, somewhat similar to the Merkel-Dumgart's construction used by SHA-1 and SHA-2, is iterative. However, there's two key differences. Number one, in Merkel-Dumgart, you take your message, you pass it through your hash function, you get the, we'll just call it the cipher, the cryptographic hash value, and then you add in the next chunk of your message, pass it through the function, etc., until you've consumed all of your message blocks, achieving the final cryptographic hash. The sponge construction, as I stated, is also iterative. However, rather than absorbing a message chunk, which then becomes the internal state of your hash function, the sponge construction has two different sections of internal state, the capacity and the rate. The capacity is what we will be adding, or is what we add in our message blocks to. We then, for every round, perform our hash function, but we perform it over the rate and the capacity. And we do this for every message chunk until finally all our message chunks are consumed and we begin what's called the squeeze phase. In this phase, we are actually emitting a hash value equal in size to our capacity. It's taken right from our capacity, and then we run the function again, and we get a new hash function, or a new hash block to add on to our previous one. And we can do this, n number of times. The sponge construction supports extendable output. So the power of this is that you're continuously running your function, your hash function, between every single addition of a message block and every single emittance of a message block. And this, at least to me, seems to be quite a powerful feature. But the NIST's recommendation for the implementation of SHA-3 says, okay, you can absorb all your message blocks and you only have one cryptographic hash output. Now, that same documentation, that same NIST document says that there are multiple versions of SHA-3 that you can use. The extendable output version, something they call shake, allows you to do n number of squeeze steps. However, that appears mostly to be a form of random number generation, or a generation of a random stream, rather than producing a cryptographic hash value. And for a long time that confused me because, again, this seems to be extremely powerful. You absorb, continuously run your function, and squeeze running this function. So this led to the question at the start of the video: why does the NIST documentation say, or for SHA-3, why does it say that we don't perform multiple squeeze steps? Why do we only perform one? And this is where my argument is mostly conjecture rather than a hard-proven fact. But it appears to be that when you are running SHA-3 and you are emitting your cryptographic hashes, you are actually giving up at every step more secret information. Now, I'm going to get into this in a second, but my point here is, and the NIST documentation, and even the documentation for the cryptographic hash function who actually won the SHA-3 competition, Ketchak, they imagine the internal state of SHA-3 as a cube. Now, I've only drawn one dimension of it for simplicity's sake, because I think this still proves the point. But you're only emitting this portion of the internal state. Again, this is the capacity. Now, when you emit it, if this were in the Merkel-Dumgart construction, this cryptographic hash would be the cryptographic hash of all your message blocks. As you can see at SHA-3, though, we have all this information floating up in the air here. This is all locked up in our rate, which, if we follow the SHA-3 recommendation, the NIST documentation, we don't emit these. We just simply emit this, and all this is left secret, such that this information is kept safe, and only somebody that actually knew the original document in its complete correctness would be able to produce the same hash. Now, what's interesting, though, is if you apply the function, those bits are getting shuffled around again inside that internal state. And again, we're going to get into this for those of you that know, but not all those bits are necessarily going to change. And even if they do, if you, as, let's say, somebody nefarious, let's say Oscar, if you have this information and then this information, you might be able to make some sort of mapping going, hey, look, I know for a fact by following this function that whatever bit's here was created by using these bits somewhere around here. And for every single iteration following in the squeeze step, you'd be able to potentially monitor and make guesses at these bits by simply seeing which bits come out of here. Now, this is where this comes into play. So Ketchuk was the winner of the SHA-3 competition. SHA-3 is actually a version of Ketchuk with certain hyperparameters that I'm not going to get into, but I do want to briefly go over the core of Ketchuk, which are these 3 steps. Step theta is really a XORing of parity bits across the columns. So you take column 1's parity, column 2's parity, and then for every bit in a particular column, you'd XOR that parity bit. Now, rho and pi combined, their essential impact upon the internal state of SHA-3 is to simply shuffle the columns of the internal state and rotate them. So it's just shuffling the bits around. It's not actually changing them. Now, the chi function, however, somewhat similar to theta, we're actually looking at other bit values and then XORing them together. So we're performing some change. The iota step is simply using an LFSR or a pre-computed table of values and XORing them into the state. So this step you can easily work back from. Now, these 2 steps are your real heavy hitters, the real introduction of information that is hard to unwind. However, it is possible to take guesses at the possible values resulting from these individual steps. Somebody's actually done work at looking at a side channel attack against Ketchuk using power analysis and showing you can actually see the different bits and what happens, and it's possible to work your way back. You can make guesses. I mean, after all, this is not a, this wouldn't necessarily get you the original value or allow you to necessarily make an attack in one easy go, but you can start making educated guesses perhaps. And so, again, this is why this is all conjecture. My theory being that the reason why the NIST's recommendation for a SHA-3 implementation says the usual only generate one cryptographic hash value is you want to be able to prevent people from making guesses like this. Now, are they useful guesses or not? I can't tell you that. But it seems to be that if you start emitting this secret information, even if it gets shuffled in, you are leaking secrets. And this seems to be perhaps probably the most powerful feature of the sponge construction in regards to cryptographic hashes, is that if you're only emitting this one cryptographic hash, you have all this information that's secret, right? So a major problem with Merkle-Damgard is length extension attacks. Well, you can't do that in a sponge construction simply because the attacker doesn't have this information. In Merkle-Damgard, they have the totality of the cryptographic hash, meaning that they have all this data, if you will. Now in SHA-3 though, in the sponge construction, we are hiding some of it away, such that only the people that know the original value or have the original value and want to generate a hash, etc., are able to actually create the real hash, and that the attacker has to guess at all these bits. So there you go. That is my conjecture about why the SHA-3 implementation, or why the SHA-3 recommendation by NIST only emits one cryptographic hash value during the squeeze step of the cryptographic sponge construction. Thank you.